The lovely thing about a vector space is that it has a basis, and this makes it super easy to understand how linear maps work. So the only functions that we're interested in are linear maps, and they're actually quite simple. So, big idea. Once you know how a linear map acts on a basis, know how a linear map acts on a basis, you know everything about it. By which I mean you know how it acts on any vector. And so, suppose we have just some function t from v to w, and suppose we know that v1 through vn is a basis of v. Then if t is a linear map, let me back up there. Let's suppose one other thing. So suppose that t of vj is wj for each j. Oh man, now I'm out of space. Dang it. Okay, so now if t is linear, then for a general vector u, we know that we can express u in terms of the basis. So there's some coefficients aj such that if we add them up, we'll get u. And so now I can see what t does to u. So a moment ago, just back up here, I told you that once we know how it acts on a basis, then we know how it acts on any vector, right? Okay, so here is our any vector. And so how does it act on this random vector here? Well, we express it first in terms of the basis. And so I'm just substituting that in for u. Then we use linearity. So this is by linearity. And then I know what t of vj is. It's wj. Okay, and so so I know exactly what t does to u. And conversely, say if we don't necessarily know that t is linear, but we define a map. If actually here, let me back up. If we have a basis of v, and we have a basis of w, and then I just define t of a generic element of V, which we know can be expressed in terms of the basis, to be equal to, and then just swap out the V's with the W's like this, then that is going to be a linear map and it's a linear map that sends Vj to Wj. So this is actually the content of what the book calls theorem 3.5. So this says that suppose we have a basis of V and a basis of W. Then there's a unique linear map T from V to W that satisfies T of Vj equals Wj. And I should mention here that W doesn't have to have the same dimension as V. So I wrote N there, but it could be M. Okay, and that linear map in question is exactly the one that I wrote earlier. So if you have some element expressed in terms of the basis, then you just define T to be the thing that swaps basis vectors, and it will be a linear map, and it will satisfy those equations, TVj equals Wj. And that's the only thing that does that. So the book has a rather long proof of this. They go through all the details. I'm going to spare you that. I think it's pretty straightforward, so you should probably be able to read it on your own.